Hello again. Talking about seismic motions, we had the first part of the lecture. Now we're going to look at some of the modeling. How do you produce those realistic 3-dimensional 6-component motions? 6-component because there are always 2 horizontal components, 1 vertical component, but there are also rotations about this axis and about this axis. And so when you combine those, you end up with a very complicated, sophisticated earthquake picture. So let me start sharing my screen. Okay. So let's look at some of these regional geophysical models that are used to model realistically earthquake motions. One important component is that modeling of or knowledge of geology is very important, both shallow and deep geology. Usually for projects that are not that important, people skip that, or they even don't look at some geologic maps. But for important objects like dams or nuclear power plants, or maybe large bridges, it's important to know what the geology is like beneath, because different geology can make a difference in response of the soil structure system. So here's a simple example that we played with a while ago. Let's assume you have actually fairly simple geology, just a few layers down here. And let's say that in real life, there are 6-component or 6D motions that are coming at an angle. They interact with the surface and they produce surface waves and so on. And this is a location where we record. We're trying to record at this location, and we record horizontal components of motions, we record vertical components of motions, and we record rotational components. When I say rotational components, I mean difference between 2 components, 2 points that are fairly close. They're going to go up and down with some phase lag, and that's going to produce essentially rotational component of motions. So we'll go back to this example, to this model. Let's run it again. Again, it's sort of realistic and unrealistic in the sense that there's a point source here, which is sort of unrealistic. Usually when we model these earthquakes, we actually have a line of sources, and then we sort of propagate that way. But this is just a simpler way of that line. They're all going to be superimposed. In this case, we just have a single point source, and that point source produces waves, and they reflect and refract at the boundaries of layers, and then they interact with the surface, and then they produce surface motions and body waves and so on. Again, let's look at this location right here, location of interest where the future object is going to be. So let's go to the next slide. So the wave is coming from beneath, interacts with surface, and produces both horizontal and vertical motions. And if you look at 2 points nearby, you see that these are going to have some rotational effects. So now we use these motions that we produced actually using a simple finite element program, essentially in 2D, using Real-ESSI. And we can now claim that this is a small geophysical model. It's not that large. It's 750 meters by about 1.5 kilometers. It's a very shallow earthquake. We just didn't want to go into too much details of geology, but these are realistic motions. So if you go forward, you can actually take those motions, the motions that we produced here, and use the so-called domain reduction method that we have not covered yet. We're going to cover that in a lecture, maybe 2-3 lectures, and develop a much smaller model that's going to take these motions and produce so-called effective forces. And those effective forces are going to be used to apply domain reduction method forces and produce motions like this. This is a model, a free field model, that is using a DRM layer right here, and right here. And again, I'll do full derivation in a couple lectures. But the important thing is that these motions here, the ones that you observe here, are exactly the same to these motions here. And my computer got stuck a little bit. They're exactly the same at this area here on the, let's go back. They're exactly the same as motions here. We actually did compare that analytically. We took a number of points and we compared these motions. So motions that you observe here are exactly the same. They're applied using so-called domain reduction method that was developed by Jacobo Bielak and his colleagues about almost 20 years ago. Now, one point I'm trying to make is this. Let's take a look at this one point here, and let's pretend that we record all motions, all the three components and rotational component. Let's pretend we only record horizontal component of motions. What we can do with that horizontal component of motions is we can produce one component wave, vertically propagating shear wave, that is going to mimic exactly motions at this point. They're going to be exactly the same. Horizontal motions are going to be exactly the same as the motions here. And we get excellent fit in this one component. We get excellent fit, but wrong physics. So let's look at that again. So let me actually put these two, actually put it down here at the beginning, and I'm going to try to run this first to kind of have them synchronized. So horizontal component of motions at this location is exactly the same in both models, but they're completely different wave fields. We'll talk about that later. What does that mean for structure? We'll show examples with structural response from here. But it's an important distinction to make that 1D components of motion, 1D motions, one component motions vertically propagating shear waves, although they do reproduce horizontal motions that are observed in real life or in these models, are actually producing wrong physics. If you compare this wave field and this wave field, it's completely different. It's not even close. So let's go forward. Some colleagues from Lawrence Livermore National Lab that sits about here are producing much larger models. These are models that are regional models. This is a model that's 120 kilometers by 180 kilometers, and it goes about 40 kilometers deep. For such large models, you need a lot of points to be able to resolve wavelengths and frequencies. So they usually go to somewhat smaller models. San Francisco is here. Davis is about here, so we're always out of picture. We're not of much interest in this case. But there are some really important structures and some really important industries here in Bay Area, in Silicon Valley, San Francisco, this East and West Bay. Some really important buildings and houses up here, some really important bridges all over the place. So this model is used to look at scenarios. Of course, as I mentioned, you have to know geology. This is fairly detailed geologic map of deep geologic map of Bay Area, developed by USGS. Again, these boundaries between layers are not exactly where they are. I mean, there's always uncertainties and uncertainties in these properties, but it's a fairly good, they have a fairly good idea of what happens. For example, there was a famous Loma Prieta earthquake a long time ago that happened about here. This is Santa Cruz. The Loma Prieta was in Scotts Valley about here. This was the center. By the way, this line here, did you see? This line, this is San Andreas fault. This line here is a Hayward fault. Both of those are very sleepy in last many years. Small slips here, but there was a slip here, so 20 some years ago, Loma Prieta. We expect a large earthquake. This is supposed to slip sometime soon. We'll see when. So those are the faults. That's the Loma Prieta. It turns out a lot of damage was in San Francisco right here. It turns out there was a very stiff layer of rock, protuberance of rock, and it took most of the energy of the earthquake. And then that layer stopped here close to San Francisco, and then all that energy ended up on the surface. So geology is very, very important. So here's the model, the one I showed earlier, this model here. The upper side of the model is showing this part, and you'll actually see more motions on this side because although these are low mountains, they are soft. Here is the Bay Area. Bay Area has a lot of mud, but it's a very shallow layer of mud. There's a good rock beneath. So you actually get a lot more motions on that northeast side than on southwest side where the Bay mud is. So here's the hypocenter, the slip starts here and then it slips over the earthquake. And you see how the waves propagate. And because of local geology and local topography, there are a lot of hills and valleys, you see how waves get stuck in those valleys, and they can oscillate for dozens of seconds. So this is a fairly good model, and we can actually take, with Real-ESSI, we can take motions from these models that are produced, by the way, with a program called SW4. This was done by Rodgers, and we can take those motions, realistic motions with realistic geology, and use them for soil structure interaction. So what do we do about one component motions and about 3 times one component motions, which are becoming popular, but they're not also quite realistic, and full 3 component motions or 3 component motions with all the rotations? Well, if you look at it this way, let's say just one wave, depending on the wavelength, on the shear wave velocity or P wave velocity of the soil and rock down, and depending on the layering and depending on the wavelength, if you have an object that is this large, I don't know, power plant, 100 meters, maybe some building, 50 meters, 100 feet or something like that. If you have a really long wavelength, this object is going to go up and down, like this way. This object is going to go up and down, up and down, up and down. If you, on the other hand, have a higher frequency, lower period motions, object is going to go up and down, but it's going to rotate a lot. If you have motions that are very low wavelength, that's about the size of the object, you're actually going to see a lot of waving like this, and not much going up. Well, there will be some up and down and left, right, but there will be a lot of waving like this, which means that for tall objects, you'll get a lot of displacements up and accelerations on top, just because of these rotational components of motions. So here's one example that Hessian prepared. It's a 200 meter by 300 meter model that has all these layers on the outside. There's a DRM layer here, and what he did was to make an analytic wave at 60 degrees, inclined wave going inside, and there are waves at 1 hertz, so one type of wavelength, 2.5 hertz, 5 hertz, and 10 hertz. And by the way, there are layers at, I think, at 50 meters, and so you can see how these waves go. So Hessian, so tell us, do you remember what was the shear wave velocity of the surface? I think it was 500, right?
Yeah, I remember. Yeah. So
500. But 500. But because there are different complicated layers, 500 here at 1 hertz would make a wave be long 500 meters at 1 hertz.
Yeah, that's.
But this layer beneath, I think, is 750 or so.
1,000.
Oh, 1,000. Okay. 750 and 1,000. If it's a 1,000, then the wave length here will be 1 kilometer, and so there will be some interaction between this layer and the upper layer, and that's going to create those lonely waves. So things get complicated. This is at 1 hertz. At higher frequencies, you get much shorter wavelengths. Look at the 10 hertz. You get actually quite a short wavelengths on surface, and you get very interesting interaction. By the way, these are not real time. In real time, this 5 to 10 hertz goes very fast. These are slowed down about 10 times just to show you what happens. So can you tell us, Hessian, about these interactions here? They look very interesting.
Yeah, so because you have an inclined wave propagating through a layering system, so you will actually get, because of this reflection and refraction, you will get upward going, incident P wave, SV wave, and this wave will interact with the surface, will generate the surface wave, as you can see here, on the 5 hertz, 10 hertz, they are pretty clear. And also they will generate reflected and refracted as a downward P wave and SV wave. So this upward and downward wave will like interact together with each other. So they depends on the frequency and it depends on the inclination. They will have either positive or negative interference, wave interference. As you can see here, for example, in the 10 hertz case, you can clearly say there's a very significant positive interference at the depth at around like 50 meters, right?
Yeah. So down here, so the red blobs are very large displacements, and the blue ones are zero displacement. So there's a significant negative interference where you essentially kill displacements, and then there's also a very significant positive interference where you amplify them many times over. Yes.
Yeah.
Good, excellent.
And similarly here for 5 hertz, they have different interference point.
Yeah, of course. Well, yeah. So different wavelengths and
Yeah.
different. That's right. But there, this is at 60 degrees, so this looks one way for 60 degrees. For others, for a real earthquake, they'll come at different angles, and it will be a
Yeah.
much more
Sure.
complicated picture. But this is actually a very, very good example to show what components of those waves can do, and then you can imagine how they're going to be much more sophisticated and complicated in real life. By the way, let's
Yeah.
assume that you have an object that has a dimension of 100 meters. Let's go back. So 100 meters is about the length, almost the length of this arrow. So now imagine an object here. This object is not going to go up and down. It's going to rotate. It's going to rotate left and right, left and right. And so we'll spend actually quite a bit more time talking about motions and showing examples. So to finish, it is important to use realistic seismic motions because we eventually want to reduce modeling uncertainty. We want to know more precisely what is really going to happen to an object. Is it going to sway? Is it going to rotate? Is it going to go up and down? And this can only be done with sophisticated models. So you should be able to go to lower sophistication level, to higher sophistication level, just so that as an engineer you get the proper picture of what's happening with the object. So with that, we'll stop, and then we'll continue in next set of lectures. We're gonna talk about how to create those motions, how to solve analytically waves in plane, plane waves at single frequency, and then how to input those waves using DRM in finite element models. And then we'll eventually show also some realistic soil structure, earthquake soil structure interaction behavior, where we're going to have also plasticity that can eat up a lot of energy. And Dr. Han is going to talk, Dr. Han Yang is going to talk about how do we eat up energy. Thank you very much. See you next time.